What specific problem does Agent Q aim to solve in the context of web agents and their limitations in multi-step interactions?
Agent Q aims to address the limitations of web agents in effectively planning and reasoning during multi-step interactions, particularly in dynamic environments like real-world websites. Current large language models, LLMs, struggle with generalization in interactive settings, leading to challenges in understanding how their actions impact the environment, which is critical for autonomous agents. To overcome these issues, Agent Q combines Monte-Carlo Tree Search, MCTS, with self-critique and reinforcement learning, allowing the agent to improve through autonomous experience and limited supervision. This approach enhances the agent's ability to navigate complex tasks, such as booking reservations, by providing intermediate feedback and optimizing decision-making based on both successful and unsuccessful trajectories. Ultimately, Agent Q seeks to significantly improve the success rates of web agents in multi-step decision-making tasks, setting a new benchmark for their performance.
How does the proposed method Agent Q work? Illustrate the process step by step, highlighting the roles of Monte-Carlo Tree Search, MCTS, and Direct Preference Optimization, DPO.
The proposed method Agent Q operates through a combination of Monte-Carlo Tree Search, MCTS, and Direct Preference Optimization, DPO, to enhance the planning and reasoning capabilities of a web agent. First, the agent utilizes MCTS to explore the web environment by representing the agent's history and the current web page as nodes in a tree structure. During the selection phase, the agent samples potential actions from a base LLM and ranks them using AI feedback to guide exploration, balancing exploration and exploitation through the upper confidence bound UCB1 formula. After executing an action, the agent rolls out the trajectory until a terminal state is reached, receiving a reward based on success or failure, which is then backpropagated to update the values of the nodes traversed. Concurrently, DPO is employed to fine-tune the agent by creating preferences over action pairs based on the feedback received, allowing the agent to learn from both successful and unsuccessful trajectories, thus improving its decision-making capabilities in future interactions. This dual approach significantly enhances the agent's performance in complex web navigation tasks, as evidenced by the substantial increase in success rates during experiments.
Can you provide a specific example of how Agent Q operates in a web environment, detailing a scenario that showcases its reasoning and planning capabilities?
Agent Q operates in a web environment by utilizing a structured approach to navigate and complete tasks, such as booking a restaurant reservation on OpenTable. For instance, when tasked with making a reservation, Agent Q first receives a user instruction, like, "Book a table for 4 at Secconi's on May 22, 2024 at 7 p.m. It then generates a sequential plan of actions using its base LLM, which includes reasoning steps to determine the best course of action, such as searching for the restaurant's page, checking availability, and selecting seating options. Throughout this process, Agent Q employs Monte-Carlo Tree Search, MCTS, to explore various actions and their potential outcomes, while also integrating AI feedback to evaluate the utility of each action at every decision point. This combination of planning, reasoning, and self-critique allows Agent Q to adaptively refine its approach, ultimately achieving a high success rate in complex tasks, as evidenced by its performance improvement from an initial 18.6% to 81.7% in zero-shot scenarios on OpenTable.
What are the key theoretical and practical advantages of Agent Q compared to previous methods for training web agents, particularly in terms of performance metrics and operational safety?
Agent Q offers significant theoretical and practical advantages over previous methods for training web agents, particularly through its integration of Monte-Carlo Tree Search, MCTS, and AI-based self-critique. Theoretically, it combines search and learning, allowing for improved reasoning and planning capabilities, which are critical for navigating complex web environments. Practically, Agent Q demonstrates superior performance metrics, achieving a zero-shot success rate of 81%. 7% on the OpenTable environment, and further improving to 95. 4% with MCTS, significantly outperforming the baseline models and even GPT-4. In terms of operational safety, the use of AI feedback for process supervision helps mitigate risks associated with autonomous actions, as it provides intermediate evaluations that guide the agent's decision-making, reducing the likelihood of errors in sensitive tasks like reservations and financial transactions. Overall, Agent Q's framework not only enhances performance, but also addresses safety concerns inherent in autonomous web interactions.
How was Agent Q validated within the web shop and OpenTable environments? Discuss the experimental design and the metrics used to evaluate success rates.
Agent Q was validated in both the web shop and OpenTable environments through a series of structured experiments designed to assess its performance in completing specific tasks. In the web shop environment, the agent was evaluated on a set of 12,087 predefined tasks, with a focus on finding particular products, and success was measured by the exact product match, yielding a baseline success rate of 28.6%. The experiments included comparisons against various baselines, such as behavior cloning and reinforcement learning fine-tuned models, with Agent Q achieving a notable improvement to 55% success when equipped with Monte-Carlo Tree Search (MCTS) capabilities. In the OpenTable environment, the agent's task was to book restaurant reservations, and success was defined by 4 criteria: correct date and time, party size, user information, and completion of the reservation. Initial tests with the Llama 3 to 70B model yielded a zero-shot success rate of 18.6%, which improved to 81.7% after applying the full Agent Q pipeline, demonstrating the effectiveness of the approach in a more complex, real-world setting.
What are the main limitations of Agent Q, particularly regarding its reliance on online interactions and implications for safety-critical tasks in real-world scenarios?
The main limitations of Agent Q stem from its reliance on online interactions, which can lead to significant risks in safety-critical tasks. As highlighted in the paper, while the agent can autonomously explore and improve, it may make numerous mistakes during its search process, resulting in unsafe behaviors, particularly in sensitive environments like banking or personal information sharing. The need for significant online interactions can create challenges in credit assignment, where even minor errors can lead to incorrect final outputs. Additionally, the agent's capability to roll back actions is not always feasible in real-world settings, further complicating error correction. Consequently, these factors necessitate the implementation of additional safety measures and human oversight to mitigate potential risks associated with deploying Agent Q in critical applications.